Hey, sports fans, ready for some calculus? Hey there, and welcome to Planet Numeracy. My name is Mark Nolde, your personal math coach. Let's talk about antiderivatives. That a function, capital F, that's a big F, is an antiderivative of f, little f, on an interval I, whatever interval that may be, when f, big F prime of x is equal to little f of x for all x on that I. So what does that mean? Let's look further. To find a function f, this is big F, whose derivative is 3x squared, we think of where that derivative, this, came from. So if I took the derivative of, with respect to x, of the function x cubed, we know by now that this would equal 3x squared just by using a simple power rule. So that's the start of it. However, x cubed plus, say, I don't know, any constant, 37, my wife's favorite number. If I were to take the derivative of this function with respect to x, it would still give us 3x squared, which is what we have here. So what we have to remember is that when we take an antiderivative, there's always going to be a constant that's included with it. So let's look at a couple of examples. So let's solve this differential equation. We have y prime equals 2. Well, if I went backwards, if I said, well, where did this 2 come from? It came from a 2x. But it could have come from a 2x plus any constant. So what we usually do is just write plus c for any constant. It could be any constant. So this represents actually a family of curves. But first, let's look at the general equation. Y equals, this is called an integrand symbol, or an integral symbol. This is the integrand. This is my variable of integration. This dx tells me I have a function of x. And when I take the antiderivative, it's going to be represented by a big F. And then we will always be adding what we call the constant of integration. Now keep in mind, it doesn't have to always be F. This could have been little g and this could have been big G. It just doesn't matter. So this is kind of the format that gets followed on all of these. So without further ado, an actual example. So this is another differential equation. It says solve the differential equation. So dy dx equals 9x squared. So 9x squared means it had to have come from something x cubed. So what we're doing is we're adding 1 to the exponent. Just like when we take the derivative, we subtract 1 from the exponent. And then I divide my old coefficient by my new exponent. And the shortcut way of doing this is just saying, well, that's 3x squared. Because when I take the derivative of 3x squared, 3 times 3, that's 9, and I reduce the exponent by 1. And the last thing we have to remember is that this always gets a plus c. So the actual function I'm looking for is 3x cubed plus c. So occasionally when we're doing derivatives, or a lot of times actually, we would have to rewrite an expression in order to use our power rule. Well, when we use the what I call the reverse power rule, sometimes we'll have to rearrange this. So I'm going to rewrite that as x to the negative 3 dx. So when I go to take the antiderivative of this, I know the result's going to have an x to the negative 2. But I have to decide what do I multiply by here to get my old coefficient of 1. So I'll put that 1 in there. So if I take the old coefficient of 1 and divide by the new exponent of negative 2, we'd end up with negative 1/2. And I finish it off by writing plus c, some constant of integration. So we can check these by going backwards. What is half of 2? Well, half of 2 is 1. And negative half times negative 2 is positive 1. So this checks out. I don't have a green check. I'll put a blue check with it, though. So that one checks out. So sometimes you will have to do a little bit of rewriting. So be mindful of that. Here's another example that's going to need a little bit of rewriting before we get going with it. So I'm going to rewrite this as x to the negative 1/2. So I'm taking this x squared of x, writing it as x to the half, and then moving it upstairs with a negative exponent. The reason I do that is because then I can just simply distribute it on x plus 6. So don't forget our dx. So now I'm going to go ahead and distribute this. So this would be, let's see, x to the 1/2 plus 6x to the negative 1/2. And I guess I technically need some parentheses there, and my dx. So now I'm going to go through term by term. Looking at this term, the first term, 1 more than 1/2 is 3/2. So x to the 3/2. If I divide the old coefficient of 1 by 3/2, I get a new coefficient of 2/3, and we can check this. What's 3/2 times 2/3? Well, it's 1. Then go to the next term. This is, well, let's see, I'm not going to put a sign in yet, but I am going to write x to the positive 1/2, because 1/2 is 1 more than negative 1/2. So half of what was 6? So this gives me a 12. Or I could say the old coefficient of 6 divided by the new exponent of 1/2. That gives us a 12, and it's a positive 12. So now I'll put my sign in. But am I done yet? The answer is no. I need to add a constant of integration to that. So there's another example. They get more elaborate as we get going, but that's just to get started for beginners. Here's another polynomial for us to look at. So this one doesn't need to be rearranged, so this one's actually a little bit easier. So this would become 2x to the 4th, because 4 is 1 more than 3, and the old coefficient divided by the new exponent is 2. And we check it because 4 times 2, hey, that's 8. So we're good to go there. Let's go to the next term. Something x cubed, because we had to go up 1 from the 2. So if I divide the old coefficient of negative 9 by the new exponent of positive 3, well, I get a negative 3. So check it. 3 times negative 3, that's the negative 9. And then finally, whenever you have a constant, just stick an x on the end of it. So 4x, when it's differentiated, goes to 4. And one last thing, add your constant of integration. So here's one that maybe looks pretty complicated, but if I put everything over x to the 4th, everything in the top of this numerator, because this is where it came from, I'm just adding fractions together, and they have a common denominator of x to the 4th. So this would be 5 over x to the 4th. So that would be maybe the first step. And a lot of times when students get going in this, they'll actually skip this step here, this step, and they'll go right to this. They'll say, well, that is x to the 4th divided by x to the 4th is 1. X squared divided by x to the 4th, well, that's a negative 3x to the negative 2, because we subtract those exponents. 2 minus 4 is negative 2. Then I'm going to rewrite the final term as 5x to the negative 4th. So the reason we do this is because now everything is in the numerator here. So I can do all these. I can do the reverse power rule for each one of those. So 1, any constant comes from that many x's. So this would be equal to x, because the derivative of x is 1. Go to the next term. Let's see. I'm going to have an x to the negative 1. Be careful with negatives because you're going up 1. So this is 1 more than negative 2. So if I divide the old coefficient, negative 3, by the new exponent, negative 1, negative 3 divided by negative 1 is 3. So I'd write plus 3 in there. So we check that. Negative 1 times 3 is negative 3. So good on that term. Then the final term, let's see, we're going to have to bump this negative 4 up to a negative 3. And then if I divide the old coefficient by the new exponent, I end up with negative 5/3. So check it. Negative times negative, that's positive. And if I multiply 3 times 5/3, the 3's cancel out, leaving us with just a 5. So we're almost done. The final part of this is to add our constant of integration. So just in case you were wondering, can you do this with trigonometric functions? And the answer is, yeah, you betcha. So if I took the antiderivative of the cosine of x, 5 cosine of x, well, that came from 5 sine of x, because we know the derivative of sine is cosine. Meant to point there. The derivative of sine is cosine. So now the next term, let's see. The derivative of cosine is negative sine, but I see this term's positive, so I'm going to say that the antiderivative of sine is negative cosine. And the 4 is coming along for the ride. Remember, this is a multiplication. When you would have done the product rule, the 4 goes away on the one term. It just becomes 4 sine x. So the last thing, as always, constant of integration. So there it is with trig functions. Okay, one last trig function here. Sometimes you have to remember your stuff from pre-calculus. You have to rewrite some of these. So I'm going to rewrite this as 1 over the cosine of x. And I guess I'd be multiplying by the sine of x over the cosine of x. So see what we did there? We just said cosine times cosine. That was cosine squared x. And the sine is still on top. And we're still doing this all with respect to x. Now, rewrite it one more time. I have secant of x, because the reciprocal of cosine is secant. And I'm doing this because I see a tangent over here. So this will become the tangent of x. And the whole thing is dx. And then I know that the antiderivative, I know the derivative of secant is, I know the derivative of secant is secant tangent back here. So I have to get rid of this piece. This is my antiderivative. And then, as always, we just add a c.
I hope you got some value from that. If so, hit the like button and subscribe. And don't forget, math is not a spectator sport. The only way to learn math is to do math.